So continuing lecture 4, some of these problems you have in your notes. This one in particular is an acid-base reaction. So I'm going to go through this one pretty step by step, and then some of the other ones I'm going to have you do on your own, and then you could check your answers. So I have barium hydroxide, 25 mils, requires 37.3 milliliters of a 0.015 molar sodium HCl for a complete reaction. What is the molarity of the the hydroxide solution? So I sometimes with these, since this is an acid-base reaction, I write out the balanced chemical equation, by the way. And then I write down the information I have for each substance so I could see what I'm looking at in terms of the problem. So I have 25 mils of the barium hydroxide. I'm trying to find out its molarity. That's what I'm looking for. I was given 37.3 reacted with it at a 0.15 molar solution. So I have enough information from the hydrochloric acid to find the moles of HCl, and then I could use the balanced chemical equation and see what I could get with that. So I have 0.15 moles over liters, and I'm going to multiply that by the 37.3 in liters, so it's 0.0373 liters, and so I end up with 0.005595 moles of HCl. Okay. Well, if I have that many moles of HCl, that's in a 2-to-1 relationship with the barium hydroxide. So 0.005595 moles of HCl. I set up my relationship. For every 1 mole of barium hydroxide, I have 2 moles of HCl. So that comes out to be 0.0027975. I don't know why I have that many digits, but I do. All right, so if that's my moles of barium hydroxide, okay, I know that I had 25 mils of it in this reaction. So all I got to do is divide it by my liters to get the molarity of the barium hydroxide. So that comes out to be about 0.112 molarity with 3 significant digits. And again, please disregard all of my extra digits there. Again, as long as your number is rounded to 3 digits and you're close to my answer, you're going to be fine. So this next problem is similar. You have 0.75 molarity of sodium hydroxide with 50 mils of 0.15 molar H2SO4. So the first thing you need to do is write a balanced chemical equation and see if you could do this one. So here I have the balanced chemical equation, H2SO4 plus 2 NaOH. That's really what you need for this. And again, I wrote down the information. So I had 2 bits of information for the H2SO4. So I found the number of moles of that. I then looked at it was a 2-to-1 relationship from the balanced chemical equation. So I ended up with 0.0159 moles of sodium hydroxide. How many liters is that going to give me, or what do I need to get me to a 0.75 molar? So I've just changed where the X is located. So realize the X is going to be in liters when you get it out. So again, if I asked for it in milliliters or liters, just be careful of that. Okay, so again, this is a pretty standard, both of these examples are pretty standard acid-base neutralization reactions that you're going to see. This next one is kind of unique because you have an antacid is sodium hydrogen carbonate or sodium bicarbonate. You have a tablet, it's complete reaction, so this is neutralizing that acid. Determine the number of grams in 1 tablet. So for this one, I'll help you out a little bit with the balanced chemical equation. Again, there's not as much emphasis on these types of reactions or knowing what they are. So I would give this to you, but I sometimes don't have it in my notes. So sodium hydrogen carbonate plus HCl produces carbon dioxide, water, and sodium chloride. Everything happens to be balanced. So just take this balanced equation and see if you could calculate the grams. See if you could calculate the grams. So I took the molarity, times it by the liters to get the moles. I realized that this is in a 1-to-1 relationship, so that's the moles of the sodium hydrogen carbonate. So then I just add up the molar mass, which is around 84, and I should get about 0.4 grams of that to neutralize that amount of HCl. So this next one is a sucrose is mixed with so much water. Do note that you will see occasionally I have MW, which is molecular weight. That's the same as molar mass. There is technically a difference, but we don't talk about that in this class too much. The mixture totals 1 decimeter, so realize that that's a liter. Again, that seems to be a popular unit that's being used a little bit more, so that's why I try to show it to you. So this one, find the density and find the molarity of the solution. So remember, density is going to be grams per milliliter. Molarity is moles over liter. So if you were asked to find the density, all you have to do is add up the sucrose and the water and take those two and add them together and divide it by the number of milliliters. Again, 1 cubic decimeter is the same as a liter, so it's going to be 1,000 milliliters. So when you divide it all out, you may not be able to read my handwriting there, it's 1.04 grams per milliliter. That seems logical because what's the density of water at 25 degrees Celsius is approximately 1 gram per milliliter. So if you're dumping sugar into water, your density should be above 1, and it's probably not going to be that much above 1 just because of solution formation. Molarity is going to be, again, you're going to take the sucrose divided by the molar mass, find the moles divided by a liter, you get about 0.288 molarity for that. All right, so this last thing I want to discuss has to do with the solutions themselves in terms of what does it actually look like in terms of the beaker. So find the molarity concentration of all the ions in a 0.3 molar ammonium phosphate solution. Okay, so if you want to write in solution. Okay, so draw yourself a beaker over on the side here. And then I'm going to write out kind of what I was talking about earlier in the lecture series here. So ammonium phosphate is NH4. There's 3 of them because phosphate happens to be a -3. And this is in water. So I'm going to have essentially 3 ammonia ions and 1 phosphate ion floating around in there. So when you draw it in the beaker, what I want you to show me is that you have 3 ammonia ions, NH4+, and then only 1 phosphate ion in there. Okay, so again, trying to show the relationship between the 3 and the 1. So if I have a 0.3 molar concentration label on this solution, what does that mean in terms of the ions that are floating around in there? But again, I'm hoping the picture helps you with this. So realize that every NH4 is essentially 0.3. So you see that 3 times more often than you do the phosphate. So it's 3 times more concentrated with the ammonia than it is the phosphate. So that means the concentration of the ammonium ion is about 0.9 and the phosphate is 0.3. Again, keep in mind that the concentration on the bottle is never going to be an additive process. Instead, what you're looking at is the individual ions and what is in